next talk is by Jamil Sater and Sean Ryan, looking at advances in ICP mass spec technology and the application of multi-element geochemistry to exploration. The talk will be presented by Jamil, who completed his undergraduate degree at the University of Saskatchewan in 2001. He also completed his master's degree from the University of Texas in 2004 and his PhD from the University of Ottawa in 2010. He has a broad experience base applying field and laboratory analytical methods to mineral exploration projects for diamonds, precious metals, and base metals. He has held a variety of technical geochemistry positions with research institutions and as a mineral exploration geochemist with small and large cap companies, including the Americans Geochemist with MMG Resources from 2011 to 2015. Since 2015, Jamil has been with Bureau Veritas Commodities Canada as the corporate geochemist and as part of the global technical governance team for the upstream minerals division. Jamil.
Thank you, John. Okay, I think we're good. Okay, I'd just like to acknowledge my co-author here, Sean Ryan. Unfortunately, he couldn't be here today, so it's just me. Okay, so first of all, I wanted to have a slide to just go through what an ICP MS actually is and how it works. I just want to, I think that most of the people in the room here understand what it is, but maybe a very quick refresher. So first of all, a sample passes through a nebulizer into a spray chamber with a carrier gas. So this type of sample could be a water sample, it could be a digested rock sample, and that sample moves through this nebulizer here with this carrier gas into this spray chamber right here. Next, that spray and argon carrier gas moves through a high temperature plasma flame, and it's very, very hot. It's burning between 6,000 and 10,000 kelvins, and it's an argon plasma flame. And at this point, this is where the mist is dried, atomized, and ionized. Thirdly, as that sample moves on, it moves through the interface and onto the ion lens right here. And at this point, the ions are separated from the positive ions are separated from the neutral ions, and those neutral ions are pushed off to the side, and then the positive ions travel through into the quadrupole. Now this is an example of a quadrupole up here, and this is what it looks like inside the ICP MS. And as you can see, there's 4 poles right there. And the way that works is that there are alternating AC and DC voltages at opposite pairs. And depending on what the voltage is, it becomes an electrostatic filter for a particular ion. And it just permits one ion at a time to move through to the detector. Now I just wanted to have a quick slide on the history of ICP MS. And there were a lot of developments in the 80s and 90s. And really the first commercially available ICP MS was 1983. That was the Perkin-Elmer-Sykes Elan 250. And it didn't take long before ICP MS was applied to the geosciences, at least with commercially available instruments. And again, it didn't take long before it was implemented or started to be implemented in exploration geochemistry. By the early 1990s, there was heavy investment in ICP MS by commercial laboratories, and there were several packages, analytical packages, that became commonplace at this point. Then in 1999 was the first commercially available collision cell ICP MS. And then most recently in 2012 was the first commercially available triple quad ICP MS. So now I just want to have a quick slide to go through what developments there were in ICP MS between 97 and 2007. And this was really, I think, a very important period for ICP-MS, and because it was a point where there was just these huge advancements related to mineral exploration, and a lot of times those advancements were related to the availability of these multi-element, low detection, inexpensive trace to ultra trace methods. And it was really a breakout, I think, for methods like soil partial extraction, ground and surface water, and biogeochemistry. And to give you an example, I've got an example here from Piercy 2013, where he is using trace element geochemistry to determine how proximal or distal you are from a VMS deposit in shales. Another example from Halley 2007, where he's been using trace element geochemistry, and then another one from Cameron and Laybourne in 2005, where selenium was used as a pathfinder or a tracer element for groundwater related to a buried porphyry system. So as you can see here, selenium values are at or below detection limit, and then as those waters move in this direction, they pick up that signal from the porphyry, and you get an anomalous signature. 2007 to 2007, 97 to 2007. Also saw significant decreases in detection limits with high-res and multi-collector analytical instruments. So now what happened from 2007 to 2017? So collision and reaction cells. These became a lot more common in the last 10 years. They're not new technology, but it has been implemented more by commercial laboratories. So reaction cells, as an example, can remove isobaric interferences, and I give the example of mercury 204 in the +1 valence state on lead 204, and that can be removed by ammonia as it neutralizes that mercury to a neutral valence state. And as it does that, then it changes the mass to charge ratio, and therefore it's no longer interfering. And as Matt described earlier today, lead isotopes are very useful for exploration as a fingerprinting tool. I've just given an example here of Godwin 1990, where he's shown two very specific populations, looking at lead 206, 204 versus 207, 204. Then collision cells also have been a lot more common in the last 10 years, and by commercial laboratories. I have an example here of polyatomic interference removals, and as an example, some of the common ones. Some of the common ones are arsenic on argon 40 and chlorine 15. And the collision cells work where the gas, excuse me, where the collision cell reacts where the gas collides with these polyatomic ions, and through kinetic processes that separates out and removes those polyatomic interferences. In terms of exploration, this results in lower detection limits for some elements, as I've got here with common interferences. So the next one is laser ablation ICP MS, and there's really two types of lasers that are currently being used. One's a neodymium doped yttrium aluminum garnet laser, and the other one is an excimer laser. There's been significant innovations in the compact excimer gas lasers, and that's resulted in a much cheaper and more affordable technology. And I've got some examples here where laser ablation has been used for spot analysis. I'll give an example here of Large 2013, where pyrite has been used in a shale basin to determine whether that basin is likely to be gold barren or gold fertile. I've got another example here from DARE 2012, where they've determined the difference in magnetite composition from an iron-rich monosulfide solution versus magnetite from a residual copper-rich intermediate sulfide solution. And it can also be used to create element maps, which can be used for element deportment, mineral associations, inclusions, and so on. I won't spend too much time on this slide, but because this has already been talked about, I think, earlier today by Dave Cook. And just another example of how laser ablation can be used. And in this case, it's the green rocks, where spot analysis has been done on epidote. And also, I just wanted to, I've got this clip here from the internet, from a website, mining news website, which describes how Rio Tinto has really embraced this type of technology, and as of 2015, we're offering it free to junior companies to facilitate exploration. Laser ablation can also be used for lithogeochemistry, and that's where a fused glass bead can be ablated. And there's definitely some benefits to a normal whole rock or lithogeochemical analysis. And basically, you can get total analysis at trace and ultratrace levels that's comparable to a 4-acid ICP MS package. If you include XRF with the laser ablation, then you end up with a very large dynamic range from the ppb level to percent level. So that negates the need for overlimits for many elements. It's simple. It's one analysis and one digestion. And there's also an environmental aspect to this as well, because it minimizes hazards using nasty chemicals like HF and perchloric. So how much has changed since 2007? So I've showed how collision reaction cells can be used and how laser ablation is being used by commercial laboratories. But really, for the most part, the routine analysis that are requested by people submitting samples to laboratories hasn't changed substantially in the last 10 years. You're still getting the same packages being requested with the same detection limits and the same methodologies that were being used 10 years ago, and that's dominantly the case. So I've just put out some reasons as to why this might be still the case. So the exploration community might still be trying to explore how best to use the currently reported data in order to extract full value out of it. There is possibly a perception that new methods result in potentially higher costs and don't provide significant value. One example of that is laser ablation. Historically, laser ablation was very expensive and was in the domain of universities and research institutions only, and it was considered something that was very expensive because a lot of times it was used for uranium-lead dating on zircons and so on and so forth. But that's not necessarily the case today. It's certainly a lot cheaper than it used to be. And then currently available commercial ICP MS offerings might still be fit for purpose and might be satisfactory for the type of investigations and programs that are being currently run. So this can all be distilled down to one equation, and that's value equals quality times information divided by cost. So then what is driving innovation? And I just, I put this first one up here because we really do work in a bipolar bipolar industry. It's either really, really good or it's really, really bad. And it's not very often that we get that Goldilocks moment where things are just right. And so the case for the last 5 years, since 2012, has been that we've obviously been in a very large and long slump. And that could have impacted the amount of innovation that's being done by laboratories, because there's less money to spend, there's less clients requesting certain methods, and then on the client side and on the people submitting the samples, well, they're just not doing the work, so they're not thinking in those type of ways either. And I've got an interesting chart here that I can show. And what I've got in blue is an AQ250 method. That's a BV method, trace element, aqua regia digestion that's commonly used in exploration. And then right here, I've got the total spend in exploration for non-ferrous minerals globally. And what you can see is in 2012, it peaked at $22 billion. And at that point was a pretty high point also for the number of samples that were received by Bureau Veritas. Throughout the next 4 to 5 years, we can see that plummets. It's down to, in 2016, that exploration spend was nearly $7 billion. So that's almost 1/3 of what it was before. And that also corresponds with a steep decrease in the number of samples that were submitted as well. Other exploration or other drivers could be that in environmental geochemistry, for example, there are regulatory requirements that can spur innovation and application of new technologies. And we don't necessarily see that as often in exploration. So prediction for the next 10 years, I see greater application of collision and reaction cells, of laser ablation, and also more innovation and more application of triple quad ICP MS instruments, especially for the isotopes, as Matt had talked about. But one thing to remember is that new methods, especially with low detection limits, require changes and modifications to collection methods as well, because you're only as good as the sample that you collect and how you collect it. And also increase in management of big data through AI applications. I'm going to move on here now to a couple of case studies. One is the White Gold District in the Yukon. There's a long history of gold mining and exploration activity. Klondike gold fields were here in this region. Okay. I'm going to have to move through this a little quickly. So I'm just going to move through to the next slide. This I just put here because I like to think that we're doing exploration a whole lot better than we were doing 100 years ago. The geology of the White Gold District is basically a collisional event where the Yukon-Canada terrain accreted onto the North American plate in the mid-Jurassic. Gold mineralization event occurred during the mid-Cretaceous and is considered an orogenic gold mineralization. So there's a couple of key reasons for Ryan Wood's exploration success in the White Gold District. One is an orientation survey, which is nothing new, but he actually took the time to do an orientation survey, and he realized that it wasn't actually the upper B horizon that was the best horizon. It was actually the lower B to the upper C horizon. He also realized that whole area had been unglaciated in the last 55 million years, so there's no transported till. It's basically a regolith. The third reason was the use of multi-element geochemistry and by an analysis by ICP MS. And he used a unique aqua regia, and it was also involved thorough interpretation and application of those results. So just quick slide on that 1:1:1 aqua regia, and what we see here is it's a 15-gram aqua regia, and there's very negligible bias in that compared to fire assay. The aqua regia also provided, as I said, a large multi-element suite and was very reasonably priced. It was only a little bit more expensive than just doing a fire assay. So there was a real benefit in using the aqua regia rather than a fire assay. Some element vectors that were used for mineralization. He used your typical vectors of gold, antimony, arsenic. And this provided a valuable fingerprinting tool. He also used other elements such as uranium and nickel to determine the different lithologies. And then I'm just going to skip over this, but what I wanted to go to here is the conclusion. And basically, ICP MS technologies have advanced significantly, but the choices for analytical methods have really not changed in the last 10 years. And I think that a better understanding of how to extract value is needed for these large element suites. And also in conclusion, the availability of large multi-element low detection ICP MS packages have certainly contributed to several exploration discoveries. Thank you.
Well, Jamil, thank you very much.
I don't think it's actually impacted much at all. The way that I see it being used and implemented is that it helps the exploration groups on site determine whether they want to move on to another drill hole or whether they want to continue where they're at. But really, an exploration group has a set budget for drilling and for analytical work, and I see the portable tools as just an instrument in such that they can make their exploration program more efficient, and they can collect better samples. So I don't think that there's much of a change.